Okay, great. Right, let's get started then. So today, broadly going to cover two parts. I'm going to introduce myself a bit, to tell you a little bit about my background and my motivations for fluid mechanics, why I think it's the best subject, why I hope that you'll all agree with that by the end of this module. And I'll talk a bit more about the course, what we hope to achieve, how we hope to achieve it, and how we hope to make this as interactive and as interesting a learning experience as possible for you. We'll try out a few of the tools as we go as well. And then, depending on how we're going, we might have a short break, or there'll be a short kind of short exercise for you to do, where we'll start to discuss some of the ideas behind the basics of fluid mechanics, in particular continuum assumption, and we'll introduce some of the main thermodynamic quantities of interest as well. And then I'll set you off with a couple of questions before Friday's session. Okay. Right, so with the introduction. So my research. Well, I believe it or not, I was a student in Manchester a long time ago. I did the aerospace course, and I think I started with a very kind of strong interest in aerospace, but it was more a technical interest. And as the course developed, I realized that my interest lied in fluid mechanics rather than any one particular technology. And that's because fluid mechanics is such a powerful topic that it covers so many things in our everyday life. And throughout my, after I did my studies, I realized that my main interest was in this area, and I explored the possibility to investigate other applications. The thing that I really love about fluid mechanics is the fact that with one set of equations, with one understanding, we can contribute to so many different areas of science and technology. Started in aircraft, did a number of research projects looking at trying to reduce the drag of in particular, commercial transport. But then I moved to automotive and did some projects with Jaguar Land Rover, and also some motorsports projects as well, where the challenge was very similar. You're looking to try and understand the aerodynamics around complex shapes. The speed's a little bit different, but the equations more or less were the same. And more recently, I've also started to look at biomechanics as well, cardiovascular flow, which looks completely different. It's an internal flow. The flow is probably quite a lot slower most of the time, but the equations are the same. And so this is a perfect example about how versatile fluid mechanics equations are. I think the other thing that's really great about fluid mechanics is that because it's involved in so much of the outside world, it's just there in industry. And throughout my work, I've been involved in a lot of projects with industry, ranging from energy to tech sectors, as well as the aerospace and the automotive. And it's just been really a great experience in terms of how versatile the equations are. I'll talk a little bit more about some of the things. So fluid mechanics is everywhere, and to convince you, I've got two pictures here, and this is really the idea behind what we're going to drive at in this module. That once you understand the main equations, you can see patterns and shapes that are essentially reproduced all the way throughout our world. In this example, you've got a vortex system, which is essentially identical regardless of the scale. And we're going to start to introduce some of the concepts that are behind the fundamental laws, which allow you to non-dimensionalize the observations and the understandings, so that you can study the flow in a toilet, in a weather system, and understand them directly using the same concepts. Fluid mechanics is indeed everywhere, but I think what really brought me into it was turbulence. This is a video that I find fascinating. I'm sure you all will have heard of turbulence, but you probably may not all have really appreciated exactly the intricacy and the detail that's happening in a turbulent flow. This video is a high performance computer simulation of exactly what's going on in a turbulent boundary layer. It's at the time that it was published, it was amongst the most detailed, most ambitious simulations that had ever been attempted. And what you're seeing here as you go into the video, you see the flow become more chaotic as you go further down the boundary layer. The flow becomes more and more turbulent, and the boundary layer becomes thicker. And what is really striking is the intricate detail of the structure of the turbulence. And this was run on one of the largest supercomputers in the world. It took up the entire facility for several weeks, and it was seen as a really fundamental science investigation to really understand in detail a turbulent boundary layer. But to put it into context, this incredible, amazing, feat of computational fluid dynamics, as it's known, really in a practical world is quite limited. That entire domain probably represents something around the size of the yellow rectangle on the wing of a commercial aircraft in cruise. It's really a small part, and to put that in context, it would be essentially impossible beyond the limits of our computational capabilities, as globally almost, for the next at least 50 to 100 years. Such are the complexities of trying to simulate the flow around a single aircraft, and let alone the flow around a country, and to be able to get accurate weather conditions. So really, the beauty of fluid mechanics, from my point of view, is the intricacy and the multi-scale that it operates on. Here's an example from some recent research we did in the flow through an aorta. So we got, actually, these images were scanned from the PhD student that ran the simulation. He was able, in Manchester, we've got a very good MRI facility, so he was able to get some MRI images of his own aorta, and then we did the same kind of computational simulation of the flow as the periodic flow as the flow enters the aorta from the exit of the heart. And again, in something that you would potentially consider to be a straightforward flow, you can see the intricacy and the pattern of the structure of the vorticity. And it's not just something that's limited to high Reynolds number. It's all around us, and potentially it's because it's invisible most of the time, we don't fully appreciate what's happening. So there's a bit about my motivation for this topic, and I hope to enthuse you, at least some of you, with that as we go through the course. And there'll be a number of different ways that we'll be trying to do that. But this is the detail of the actual module and how we're going to deliver it this semester. So as you will know, this is actually your third week. You've had a couple of weeks of induction, and we are in the third week. We're now at the point where we started the teaching. So the teaching is going to be delivered in two parts by myself and by Ben, who introduced himself at the beginning. And then we're going to kind of revert to part one, where I'll deliver a revision session in the last week before Christmas break. And then we'll have a test towards the end of the first exam week, when we come back after Christmas. Then we'll switch to the revision of the part two, and then there'll be a test. Now, the exact details of the test aren't exactly finalized yet, but as soon as we have those details, we'll share them with you. What is finalized is how the assessment activities will be broken down. We're going to release a coursework activity in 3 weeks' time, which will be either a handwritten or a Word document that we're going to ask you to complete and upload, and will be marked in the same level of detail that we'll be marking the exam, to give you an appreciation of how we go through that process. And then we will we'll also provide model answers as well. In going into the second part of the course, there'll be a chance to do a virtual lab. Now, as you all know, unfortunately, we're restricted to our campus access, but we are at least able to offer you a virtual access. So some of our GTAs will be acting as avatars for you, and you'll be split into groups, I think of around 8 to 10, and you will be linking with our GTAs as they do some experiments on some wind tunnels and some and actually some 3D interactive CFD experiments as well. You'll have a chance to do that in the second half of the semester. This will be assessed just by a turn up and participation mark, and those that engage will get their 5%. And finally, as you'll see, this is an 80-20 split. The last 5% of the coursework is going to be awarded to people that have finished all of the weekly quizzes, and a little bit more about that later. But not just finished, we're going to make sure that we're going to require that you get at least 80% correct in all of these quizzes. And each week of the 10 weeks, there'll be a short quiz that will be on Blackboard. You'll be able to take the test as many times as you like. But in order to get qualified for the mark, we're going to tot all of the marks up and make sure that you've got at least 80% right. And that basically ensures that you've interacted with the questions. And if you've had any queries, then we've given you a chance to answer them. Just as we go, if there are any questions that are popping up, please do start to ask them in the piazza, as you can see here. So put some questions up in the live Q&A. If you've got any questions about the structure, we'll make sure that we follow them up. So then the 80% notional examination mark will be split into two halves, 40% each time, to allow you to focus on what's going to be coming up in the content, and also to not make it too long of a test for you. In terms of how we support your working, the work examples, which are such an important part of this module, we're going to have 5 tutorial sessions, which are going to be run by pairs of GTAs. The first one of which is going to be at the end of semester S+5, week S+5, and it'll be on the Friday. Unfortunately, it's the last hour of the day, 4 till 5, but it's a chance for you to see how someone else solves it. As I go through the course, I'll be giving you some work examples, particularly on a Friday, and I'll be recording, short worked examples as we go as well, to, in answer to any questions that you might have. But I find, and I think most people find, that it's generally very useful and very instructive to see how someone else solves the question and approaches the question. So this is going to be a chance for you to see how some of our GTAs, who have all sorts of backgrounds in terms of the subjects that they have and the ways that they've learned some of this content, approach these questions. There's going to be 5 of those. I'll release the first set of questions next week, and so you'll have a week and a half to engage with those. We're also going to have we've got the forum, which I'll go into in a little bit, and we've got our office hour as well. So there's plenty of ways to reach us and to interact with us. Okay. So I'll come back to the forum shortly, but for now, let's just spend a little bit more time on actually what the course is going to cover. So in part 1, this is very much an introduction to fluid mechanics, and we want to approach it with the right level of detail, but also from the beginning. As you go through your courses, we've got mechanical and aerospace engineering courses here. They're a little bit different, but essentially the fluid mechanics strand is the same all the way through. As you go through, you will build and you will progress through in complexity, year on year, semester on semester, and it will feed into many of the other modules that you're going to be taught as well. Notably thermodynamics, which I think you have next semester, which really leads very nicely, follows very nicely from this one. Those of you that have maybe bought a copy of the Frank White book, that's a good investment. Those of you that are making use of the ebook, which is available, the complete ebook, which is available online on Blackboard, you will find that a useful companion throughout your degree and beyond. It will cover the vast majority of all of the modules that we will deliver in this strand. So to start with, in part 1, we'll cover basic features of a fluid, a variation of pressure in stationary fluids, hydrostatic forces on surfaces. So you could think of a dam and the forces on a submerged dam. And then we'll start to build up in complexity towards some of the more dynamic applications. And we will look at fluid subject to accelerations, principally linear accelerations, but we'll also potentially look at some rotational flows as well. And we will then start to build up the mechanics for you to take the full equations of fluid mechanics and start to apply them. So I'll finish part one by talking about the conservation of mass and momentum, two of the principal blocks of how we use fluid mechanics. And then Professor Rogers will start part two, pick up on some of the things that I would have started. Start with some of his personal interests, his research in buoyancy, surface tension, and then build on the application of the momentum equations, various very common and strong approximations that are used to these equations in order to enable them to be used very practically. It's a range of complex applications, and also start to discuss other areas of how we're going to use these equations in practice throughout the rest of the degree. So broadly then, and this is just from a synopsis of the unit specification, the four aims, I think there's 4 of the course, to make sure that you understand how important fluid mechanics is. That's really our goal here, is to really kind of pass on some of the enthusiasm and the significance of how fluid mechanics is relevant to engineering. And also to introduce you, probably you're already aware of this, but to really kind of solidify the understanding of what a continuum mechanics approach is and how it differs from other methods. To start to put all of the concepts together in a way potentially that you haven't seen before. I'm quite confident that many of you will have come across some of these equations, at least in name, before. We're going to look at the Bernoulli equations, and we'll probably introduce you to Navier-Stokes equations. But potentially you haven't seen how they connect together, and this is really what we're driving at, to allow you to see that it's not a collection of disparate theories and laws, but they're all connected. And if with a proper understanding of how to go from one assumption to another, you can really leverage the power of fluid mechanics. And yeah, so then introducing the main equations as well. Okay, so this is the book that we are using, and it's available on the on Blackboard. I just got Blackboard loaded up here, so all of you can go to the Blackboard page, and you're able to access it here via the Cortex website, which is a very nice way to kind of to access an ebook, and you're able to add annotations and notes to this, and this will stay with you throughout your degree. You can quickly jump to chapters and navigate the book like that, and you'll see that as I go through, I will give you some pre-reading each week, and we will ask that you familiarize yourself with those sections. So again, some of these will vary in complexity. This week there's quite a lot of pre-read, but most of it is quite of an introductory level, and I'm sure that you'll be familiar with some of that. As we go through, we will that amount of pre-read will vary. Sometimes there'll be some videos as well to allow you to understand some of the concepts, to assist in your understanding as we go. But in general, we won't go very much beyond chapters 1 to 3. So someone already asked me if you have to read the whole book. You won't need to for this course. Of course, if you want to, you can. But our module content will focus on the first 3. Okay, so in terms of assessment, I've gone through that already. Yeah, so there's the quiz. I wanted to show you the quiz. So each week, you'll have a chance to do a quiz. The quiz is just a basic multiple choice. The questions, there'll be around 20 each time, and you'll be able to answer the questions. You'll get some feedback as to why the questions why your answers are correct or not. And no, it's asking me to answer all of them, so I won't do it now. And then it will save the results. You'll get a mark, and we ask that you repeat that until you get you know, at least 80%, if not all of them, correct. If you have any questions that come up from that, that's you know, please just go to the discussion board and we will help you. You've got the coursework, the virtual interactive lab, which has a bit of a smoke tunnel. I think if I remember correctly, there's bits of Lego that you can stick in the smoke tunnel as a sneak preview, and the end of semester tests. Okay. I can see that some questions are being asked on the Piazza as we go. I think Andrew's doing his best to answer some. Anything that Andrew can't answer, I'll answer them later on. Well, I'll commit to spending you know, at least 2 hours each week answering these questions. And please, when you're asking a question, try to read some of the other questions first to make sure that you're not repeating someone else. Yeah, so this is how it will look on the, this is an example of the each week learning module. You'll have this each Monday to see ahead. Some of the content, like the quiz, may not be released until the Wednesday, but you'll have something like this each week. And yeah, so for the Piazza forum, I think now quite a lot of you have signed up. I can see at a glance that I have 315 enrolled. That's great. Well done, everyone. And there's still a few of you. I've got 376 on the call. So there's still a few of you that need to sign up. But I think we'll get there. So that's great. Thank you for your engagement with that. What we ask, though, is that if you have questions related to, you know, a worked example or something that you don't quite understand, that you attempt them first before you post a query to the forum. And we'd like you to, you know, try it on a pen and paper. You can always take a picture with your phone, upload the photo to the forum, and basically show what you've tried and maybe how you haven't understood it. And we're always going to be able to help you better if you do that. You can, you know, if there are any questions that you're nervous about asking, you can post a question anonymously. That's fine. You can ask questions privately, but we'd very much like you to make your questions public as much as possible, so for everyone's benefit. It's quite a useful tool. Okay, so here we go. Practice poll. Let's see if this works. I'm quite new to this platform as well, so bear with me. Make a poll, enter the choices. Multiple choices allowed there. Why do you love fluid mechanics? I'm sure there's more than one reason. And then let's give you, a day to enjoy that. And let's see, post. Week 1. I think you're also able to post questions as you go. So you might have noticed you can post questions that you can post 3 types of post in this forum. You can post a note, which is just a general observation. You can post a question, or you can post a poll. And this one, I love fluid mechanics. And why do I love it? Well, there's all sorts of reasons, and I've read them all through, and you know, I'm not embarrassed to admit that it's all of those reasons. We have some emerging answers. To prepare for high-tech engineering industries like Formula One, that's interesting to hear. But also the environmental challenge as well, that's cool. And because it looks cool, right? That, to be honest, is a big factor for me. I really like the artistic side of it. Something that isn't picking up as much interest as I thought is D, the bioengineering. I'm actually surprised that the love of mathematics is doing better than bioengineering. Okay, fair enough. That's some budding mathematicians with us. Okay, I'll leave that there. Right, how are we doing? I'll probably just go through this next slide and then we'll have a short break. I think it's a couple of slides. So in summary, we're going to try and keep our content flowing all the way through. So there'll be something for you each day of the week. I mean, that's fantastic, right? Some fluid mechanics every day of the week. On Monday, we'll be making the plan live for the week. So that will consist of a list of sections that we'd like you to read and familiarize yourself with. Additional notes if there are any, potentially some links or some short videos to accompany that. We'd also ask you to complete the previous week's quiz if you haven't already. And then on Tuesdays, there's a special treat. There'll be some kind of special short video feature exploring some of the magic of fluid mechanics each week. Nothing long, nothing particularly complicated, nothing examinable, but just a small snippets of fun, of fluids fun. On Wednesday, that's today, you'll have a live content session like this where we'll highlight the main points from the content. There'll be a chance to engage in the Piazza Q&A. On Thursday, so this is potentially a new information, and the time will probably change as we go from part 1 to part 2. But for me in part 1, every Thursday morning, 9 till 10, you can just turn up. I'll send a Zoom link later on today, and play it a bit by ear, see how high the demand is. There's no prerequisites. I'm not going to be delivering any new material, but I will be there to answer any queries you have if you want to ask a face instead of a forum. I have to be limited to that time, but we can expand according to the demand. So if there's a lot of people turning up, I can ask some of the GTAs to help a little bit of that during that slot as well. Now, on Fridays, there'll be another live session, but it'll probably focus a bit more on a practice side of the content. So be some worked examples, and every other week there'll be the tutorial as well. Okay, we'll have a short break there, a couple of minutes. I think we've probably got about 15 minutes left, so we won't have too long of a break. But just people want to go up and stretch their legs, I'll pause the share, and it's 12:32 on my clock. I'll start up again 12:34. If anyone wants to go and stretch their legs, they can. Have a look at how we're doing. Some of the questions. Oh, that's great. There's lots of interaction with the forum. That's fantastic. I can't give that one away. $375. That's great. Okay, so I will resume the share. Okay, I think everyone should have come back for now. So that we're going to very quickly start with some of the main concepts of fluid mechanics. Just to introduce you, pick out some of the important ones. Just to emphasize, we do rely on you to look at the content. there's quite a lot in this first week. There'll be less in the future weeks. If you do have any questions about it, just let us know. So, as you will no doubt have seen, because this appears probably on the 3rd page, we are starting to classify fluids and solids and liquids as things that are essentially differentiated by their resistance to a force, right? That seems fairly straightforward. If you apply a force to a static, to a solid, it can resist it with a static deflection. In contrast, you apply a force to a fluid, and it will continuously move. And in fact, the only way that it can resist this force is if you are able to provide it with some external pressure, so some kind of walls around the side. And without that, it will continuously fail, continuously move around and deform under the application of a force. And to demonstrate this, let's start a discussion on Piazza as to what is going on here. So I'm just going to see if I can do this. So new post, no. Water, not water. Okay, so what is going on here? I'm going to play the video, and I'm going to give you a few minutes to put some comments and into the box to see if you can explain this video that I'm going to show you now. So you've got here a jug with some water in it, and you've got here a jug which is not water. And if you look closely, having just said that it's fairly easy to define a fluid, something very strange is happening in the one on the right. The jug of water comes out very predictable way when you pour it. The jug of not water doesn't. I'll leave that with you, and I'll let's see what people are starting to come up with some answers here. Laminar flow. Well, they're both a low velocity, so it's not necessary to do with the laminar flow. They're probably both flowing in a laminar way. Yeah, it's a polymer. This is interesting. So what is it about it being a polymer? High viscosity, yeah, that's true. High surface tension in the not water. I'm not going to tell you exactly what the content, the substance is. I'll post that later. But it's definitely not water. Slight, just a little bit comes over the edge, and suddenly, bang, all comes out. Weird. Long chain molecule, that's it, well done. So essentially, it's a long chain molecule polymer. What's happening at a molecular level, as a little bit of the flow goes over the edge here, it's able to pull somehow the rest of the fluid due to the fact that there's long chain polymers that are connected to the rest of the mass of the fluid. In contrast, the water molecules are small enough that they're able to essentially act in isolation from the rest of the fluid. And this is really, this perspective is a really important one as we start to consider a fluid as a continuum. A fluid at a molecular level is nothing more than just a group of particles, the particles that have a position and a velocity. Thermodynamic properties like a pressure or a temperature, actually, they have very little significance to an individual molecule. More about that later, when you can start to think about what actually a pressure or a temperature is at a molecular level. In contrast, continuum mechanics is the study of the bulk motion of the particles rather than the individual. And we use and apply equations that are relevant to continuum mechanics in order to apply macro scale, so things that are happening at a practical scale far, far greater in dimension than molecular dimensions. And in fluid mechanics, we essentially ignore the molecular nature of fluid most of the time, although I just showed you a counterexample with the Dongchain polymer. So we always have to be a bit careful. So in terms of how do we measure a continuum, there's a very useful non-dimensional number called the Knudsen number, which is essentially the ratio between how closely spaced the molecules are and the length scale of the practical application. So looking at this example, Knudsen number is the ratio of the mean free path, if you like, the average distance between molecules, and d, which is, it depends on the application, but it's essentially the length scale of where the flow is going through. In this case, it's the dimension of a gap between two walls. And at the continuum range, where there's many, many, many molecules all packed together tightly, then you can see that essentially the flow acts as a continuum. It passes through this as you would expect in a flow. But at the high Knudsen number range, and above 1, you're essentially saying that the mean free path, the distance that molecules travel before colliding with each other, is essentially the same as the physical length scale of the domain. Above 1, you get all sorts of a different non-continuum behavior, and you're in the molecular regime. And this is very important in some practical applications. As you approach a vacuum, as you're in space, then essentially you have high Knudsen numbers. But for the vast, vast majority of engineering flows and practical flows of engineering relevance, like water and air, that we're going to be studying, then you're really considering very small Knudsen numbers, where essentially there isn't a gap, or we're not interested in a gap between the molecules. And you can see that by the statement that almost all flows of practical interest are below this Knudsen number range of 0.001. So it's really a small, 1,000th the ratio 1 to 1,000, the mean free path to the practical length scale. So Knudsen number is a key concept. Continuum. Another one that is really, really fundamental that I wanted to start with is viscosity. And viscosity is close to my heart because it's the root of all turbulence and the cause of all interesting things, as far as I'm concerned. Like, it's essentially a measure of the stickiness, how sticky a flow is. But it's more than that. If you start to think it at the level of the scale of the layers of the fluid, it's resistance to motion between the different layers. All fluids have viscosity of some order, except in the theoretical way. We do consider flows that are ideal fluids, and in such flows, there is no losses due to viscous forces. There is no viscosity, but this is an assumption only. In practical circumstances, there is always a loss, as you will find out in thermodynamics. And essentially, viscosity becomes really, really, really important close to a wall, because if you have a stationary wall, that wall at the molecular level is pulling and stopping the molecules that are in the flow from passing, and they come to a complete rest. So, and then translating that to a macro scale level, flow and layers of flow, or pockets of flow, come to a stop at the wall. Their velocity comes to a complete stop. It sticks to the surface, and we call this the no-slip condition, which is a fundamental condition of fluid mechanics. And you'll see this no-slip condition. You see it given in textbooks, in coursework answers all over. The velocity at the wall is 0, and that's because of viscosity. The flow is essentially brought to a complete standstill because of the viscosity between the layers.